Right, our next distribution is the hypergeometric distribution. So we saw the hypergeometric distribution earlier in our discussion of lottery examples early on. So hypergeometric distribution is the distribution we get from thinking about, let's say we have a total of capital N balls in a box. And the balls are marked, let's say M of them are white and the rest are, little m of them are white, the rest are black. And we're going to draw N of them, little n of them, without replacement. Then X, the random variable, is the number of white balls drawn. So capital N is the total number of balls. M is the number of white balls. N minus M are black balls. And N is the number of draws is less than or equal to N. So what we're doing is we're drawing we're drawing N less than N balls without replacement. From an urn containing M white balls and the rest, capital N minus M, black balls. And X, the random variable, is the number of white balls drawn in our N, little n draws. Okay, so this we would say X is hypergeometric N, M, N. Okay. So we've already calculated this before, and we've seen how we can express the mass function for each possible value of K, the number of white balls drawn. The mass function is that, well, we have N little n spot. We have little n spots to, we have little n draws. Okay. K of them are going to be white and the rest are going to be black. So for the white balls, we have to choose K spots out of the M. We have to choose K balls out of the white balls. We have to choose little n minus K balls out of the remaining black balls. And there are a total of big N choose little n, all total combinations that we could draw. Or we could consider the ordered analysis, which is that we choose the K spots that we're going to put the white balls in. We then draw them in order, and then the remaining balls, we have to draw those in order, and then out of all total orderings, which is N fall little n. And otherwise, the probability is 0. So we've seen that in order for this probability to be proper, we need K to be less than or equal to M, and N minus K to be less than or equal to N minus M. So we can't say, well, we can't draw more white balls than there are white balls in the urn. We can't draw more black balls than there are black balls in the urn. So the interesting thing here is, how are we going to calculate the expectation and variance? So at first, it's actually pretty tricky because the draws are not independent of one another. If I draw a white ball on the first draw, I'm less likely to get a white ball after that because I've removed a white ball from the urn. And so that's the nature of drawing with replacement. But what we do know is that the draws are in some sense exchangeable. So are exchangeable. And let's describe what we mean by that. So let's let xi, x1, x2, etc., up to xn indicate the outcome of the ith draw. So xi is equal to 1 if the ith draw is white, and 0 otherwise. So then, in this case, the random variable we're interested in, which is x, the total number of white balls, can be written as the sum of these xi's. Now, importantly, remember, we've seen something like this before in the binomial distribution where x was written as a sum of independent Bernoullis. What we did there was we were able to calculate the expectation of x by taking the expectation of x1 plus x2 up to xn and seeing that the expectation of a sum is the sum of the expectation. Well, we're going to use the same thing here, and it really doesn't matter that they're not independent. We can do that anyway. So that's nice. But we still have to figure out, well, what's the expectation of x1? What's the expectation of x2? And so on. And here's where exchangeability comes into play, is that the xi's are exchangeable. They're not independent, but they're exchangeable, which in this case essentially means that if we have a fixed number k1s in the sequence, any given orientation, any given ordering of them has an equal likelihood, an equal probability of happening. So for every I, the probability that xi is equal to 1, well, by exchangeability, it's just the probability that x1 is equal to 1. So what's the probability that the first draw out of the urn is white? Well, that's actually easy because there are m white balls to start and big N balls total. So, and that's true for all I. And so it's little m over n, big N. And then for all I not equal to j, what's the probability? And we'll need this for the variance in a second. Probably that both I and j are equal to 1. This is equal to the probability that both x1 and x2 are equal to 1. Well, we already know that x1 is equal to 1 with probability m over n. And then once we've drawn that first white ball, we have to draw another white ball in the second. And so there's one less white ball to draw from, and there's one less ball to draw from. Okay, so that's true for all I not equal to j. Okay. So then with that information combined, let me actually move this down. And if we move this down, what we're going to be able to do is the expectation of each xi is m over n, and there are n of these, so it's n little m over big N is the total expectation. And the variance of x is the variance of the sum which is the sum of the variances plus 2 times the sum of I not equal to j, the covariance. Okay. So what is the variance on a marginal basis? Well, what we need to do is the expectation of x times the expectation of x squared minus the expectation of x quantity squared. So what's the expectation of xi squared? Well, again, xi is a 1 or a 0. So the expectation of xi squared is actually just the same as the expectation of xi. And then the expectation of xi quantity squared is m squared over n squared. So, and then we're going to be able to, well, so then what we're left with is going to be n, so m, n minus m over n squared as the marginal variance. And for the covariance of xi, xj, what we need is the expectation of xi, xj minus the expectation of xi times the expectation of xj. Well, expectation of xi, xj, as an aside, is just 1 if xi and xj are both equal to 1 and 0 otherwise. So the expectation is just equal to this probability, which we actually already just calculated. It's m times m minus 1, calculated it right here, right here. M times m minus 1 divided by n times capital N minus 1. So this is m minus 1 over n minus 1 minus m over n squared. And so it's m minus 1 over n minus 1 minus m. Okay. So let's see. All right. So then to calculate the covariance, so I'm sorry, what am I doing here? Oh, yeah. So then what we can do is we can do a few things to rearrange. And if we do this, what we're left with is minus m over n times n minus m over n divided by n minus 1. So what we see is that this is actually negative. So the covariance is negative. And that should make sense once you think about it, because what that means is that if we know that xi is 1, then we're less likely to think that xj is 1. And that's again by the fact that if xi is 1, we know there's one less white ball in the urn to consider for xj. So then all this together gives us that the variance of x is equal to sum variance of xi plus twice sum I less than j covariance of xij. We realize that these are exchangeable, so the variance of xi is the same as the variance of x1 for all I. Covariance of xi xj is equal to covariance of x1 x2 for all I and all not equal to j, and there are n times n minus 1 over 2 of these. So what we end up with is n times big N minus little n times over n minus 1, m over n minus m over. Okay, so that's the variance. Now, one thing is that we mentioned that there is some similarity here to the binomial distribution in the sense that this random variable x is the sum of zeros and ones. It's just that instead of being a sum of independent IID zeros and ones, it's a sum of exchangeable zeros and ones. And we can actually see some relationship to the binomial in the sense that we can think of the binomial as the hypergeometric situation in which we draw from an urn with infinitely many balls, and the way that we quantify how many white balls and how many black balls there are is by the overall fraction of balls that are white as a limiting frequency. So if we define C to be this value here in our variance expression, then the variance of x is equal to C times the variance of x prime. Well, what is x prime? Well, this is where x prime is binomial with n trials and success probably m over capital N. So we think of this as this constant C as the finite population correction factor. And note that correction factor goes to 1 as n goes to infinity, which means that as the population gets bigger and bigger, we don't really need to correct for the finite population as much. And in the end, it becomes negligible, because the idea of drawing with replacement from a very, very large urn with a lot of balls, we remove a single white ball at most on a given draw. And if there's a lot of white balls in the urn to begin with, that decrement of one white ball doesn't actually change the composition of the urn in any material fashion. And so that's a way that we can think of intuitively the hypergeometric sampling without replacement as a finite case of sampling with replacement, and vice versa. Sampling with replacement is really considered the infinite limit of sampling without replacement. And so that's the hypergeometric distribution, which we found in the case of lottery examples and drawing without replacement from an urn.